Traditional structured lighting methods are not equipped to work in the presence of scattering, which is common in underwater, outdoor, and microscopic imaging applications. In these cases, the scene of interest is immersed in a scattering medium such as murky water, fog, mist, or smoke. We have extended two structured light methods, light striping and photometric stereo, to work in scattering media. Our light stripe range-finding experiments were done using a glass tank filled with scattering media, such as dilute milk, a projector, and a video camera. The desired objects are placed within the medium. The calibration of our setup requires only scans of two planar surfaces whose equations in world coordinates are measured beforehand. Here we show one of the two scans. During calibration, we compute a discrete geometric mapping between the projector and the calibration planes, and a second mapping from the camera to the calibration planes. We show the accuracy of this calibration by reconstructing a planar surface shown in green that is placed in between the two calibration planes. The RMS error in reconstruction is 0.2 inches. Our method does not require either the explicit calibration of the camera and the projector, or the knowledge of where refractions take place and the refractive indices of media. The first experiment we show uses a scene that contains two cups. When the tank is filled with dilute milk, the adverse effects of scattering are clearly seen in the floodlit image of the scene. Now, we show light stripe scanning in dilute milk. Notice the light plane itself becomes brightly visible due to scattering, which makes it difficult to detect the intersection of the light plane with the object using simple thresholding. Our algorithm detects the intersections reliably despite the rescattering and reconstructs the 3D shape of the scene. In addition, it computes the appearance of the scene without any scattering effects, as if seen through clear air. Here we show a harder example with higher milk concentration. Notice the significant backscattering and loss of contrast in the floodlit image. We now show the light stripe scan. Notice that the intersections of the stripes with the objects are very dim and are almost invisible towards the end. Even in this case, our methods perform very well. Due to strong attenuation of the light planes and the dull reflectance of the green cup, the handle of the cup is virtually invisible in the input video and hence is not detected. We now show our results for a second scene consisting of a doll and a teapot. The light striping video of the scene shows complex blooming or blurring effects due to scattering. Again, our algorithm successfully removes the effects of scattering as shown on the right side. We now show the 3D reconstruction of this scene. The second technique we consider is the popular photometric stereo method. Traditional photometric stereo computes the surface normals and albedos of a Lambertian object using 3 light sources. We have shown that in the presence of scattering, at least 5 sources are needed to compute normals and albedos. Here we show images of a teapot seen through pure water under different lighting directions. These images are shown for illustration purposes only. Now we show the same teapot seen through dilute milk. Notice the strong effects of scattering leading to significant change in appearance. If we apply the traditional photometric stereo to these images, the 3D shape obtained is very flat and the scattering effects are absorbed by the computed albedos. Now we show the results of applying our algorithm to these images. The computed 3D shape is visually accurate and the scattering effects have been removed from the albedo map. In addition to surface normals and albedos, our method also yields the depth map of the scene, which is not possible using traditional photometric stereo. In summary, we have taken a significant step toward extending structured lighting to scattering media. We believe that our results can benefit a wide range of underwater, outdoor, aerial, and microscopic imaging applications.